Hello, folks. So this is the first of a series of talks on threat models, attacks, and pitfalls. And the goal here in these talks is to equip you to be able to think about threat models, to be able to think in a structured way about these things. How do you design such a thing? This is the last missing piece of the puzzle, if you will. We talked a lot in previous weeks about security mechanisms. Last week we talked about security policies. And so the last of the three main categories in IT security, namely threat models, is what we're going to be covering here. We'll be looking at different ways to categorize attacks, and then a whole bunch of different examples of attacks, where first of all, you can probably learn from the mistakes that were made in the past, but also you can see how they fit into the categories we define. So the first talk here will be about the categories, different taxonomies for attacks. I might as well admit this is actually not the most entertaining thing to look at, just one taxonomy after the other. But on the other hand, these things can be useful because you can use them as kind of a laundry list. Did we think of all the relevant attacks? Well, we could try going through each of the categories, and did we actually think about attacks in each of those categories? And did we decide whether those attacks are relevant for us? Okay, so the first model, we could say, is something called the STRIDE model. So this is just an acronym for different kinds of goals that the attacker might be after. So what is the attacker trying to achieve here? So the S here stands for spoofing. So spoofing of identity, meaning so that means the attacker is trying to make the system believe that he's someone else than he really is, and this can then have various consequences, of course. Spoofing identities is what we're trying to avoid, of course, using passwords and biometrics and hardware devices, stuff like this. And then tampering is the T. So tampering with data is the idea. So the attacker's goal here is to be able to modify data that he's not supposed to be allowed to modify. And here we're of course relying partly on access control, but partly also on cryptography to prevent this, namely in terms of things like message authentication codes and digital signatures. Repudiation. So repudiation means the attacker is able to do something, make an action in the system, and then later on make the rest of the world believe that he didn't do this. So blame someone else, let's say. And to prevent repudiation, we have various tools. One thing would be log files, so reliable files that tell you what actually happened in the system and who initiated this action. But also things like digital signatures can be used for what is known as non-repudiation. That is, being able to prevent people from repudiate what they did. Then we have the I, which stands for information disclosure, which is just another word for the usual confidentiality notion that we have. So the adversary is able to steal information, to see information that he shouldn't be allowed to see, and of course, to do something about that goal, we have cryptography, encryption, and we have access control. Then we have denial of service. So that's what the D is for. Denial of service means the adversary manages to overwhelm the system with requests, for instance, so it goes down, it's not able to serve the actual users that it's supposed to be serving. This is, of course, not something we can. But there are ways of preventing this by replicating your service and stuff like this, making it more redundant so that it will be harder for the adversary to take down every part of your service. And finally, we have the E, which is elevation of privilege. So this just means the adversary somehow manages to get higher privileges in the system that he was supposed to have, being the user he actually is. Okay, so those are various goals the attacker might have. One remark here is they're obviously not independent. It's clear that if the adversary manages to spoof identity, then this might lead to elevation of privilege if the other identity he manages to assume actually has more rights in the system than he has himself. So that's the Stride model. Then we have a different model which comes from an international standard called X800. This is a standard from the international telephone companies, and it basically talks about, you might say, the tools of the attack. So what concrete activity is the adversary doing when he's trying to attack? It's important to say that X800 only talks about network attacks. That's what the cell phone companies, I guess, would naturally be interested in, I guess. But it also means that X800 is limited in scope. It doesn't talk about things like social engineering, for instance, when you trick people into installing malware and stuff like this. That's totally out of scope for X800. Nevertheless, let's look at what it does. So it talks about the highest level division is between passive attacks and active attacks. And those names are almost self-explanatory, I guess. So passive just means the adversary just sits there, looks at network traffic, and sees what he can learn from this. And there are two concrete ways he might get something out of what he sees. So one is eavesdropping. This should be thought of as not just the act of actually copying data from the network traffic into your own machine. It concretely means trying to make sense of what you see. So you actually try to interpret the messages that you eavesdrop and learn some data from that. And of course, to do something about that sort of an attack, we can encrypt our data to make sure the adversary can't make sense of what he sees. But even if we do this, there's also the other kind of passive attack, which is known as traffic analysis, which is sometimes overlooked, but nevertheless is actually an important kind of attack. So traffic analysis is about you simply observe who is sending to who on the network and how much do they send. And the point here is that even if you can't make sense of what you see on the network because it's encrypted, then you might still be able to learn something from the fact that that A is sending to B at this time, at this point in time, and also how much A is sending to B. This can actually contain important information. Just a very simple example: if you know that this guy is sending requests to see certain websites to another node in the network, but these URLs that he's sending are encrypted. Then, if you can learn the length of the URLs that he's requesting, you might still learn something about which web pages that this guy wants to look at. So therefore, we have various ways of trying to make that traffic pattern be less informative to the adversary. For instance, if you want to hide the fact that you're sending to one person, you can just send to a whole bunch of different persons. If what you send is encrypted, then the adversary won't see that most of what you send is dummy messages, but there's only one message that actually means something. If you want to hide the length of the data, you can send data in fixed size packages, always padding out whatever content you send to a certain fixed length. And there is then finally also a more fancy technique known as steganography, which is the idea that you hide the information you want to send inside something else. So if you take a picture, for instance, that you're sending, then it's possible there are techniques for hiding information inside such a picture. You modify slightly some of the parameters of the picture. This will not change the way the picture looks when it's rendered on screen, but a receiver who knows where to look will be able to find out where those places are and extract the message from this thing. So in this way, you can hide even the fact that the message is being sent. Not the best bandwidth you get this way for sure, but still an interesting technique in some cases, I guess. The active attacks are completely different. Of course, they are more easy to spot. Of course, because here the adversary is actually modifying the traffic on the network, but the consequences can also be worse. So an active attack, you can split those in different types. You have modification, you have blocking, and we have replay. So modification simply means the adversary looks at the traffic he sees and modifies it, flips some bits, or even invents a message completely of his own and sends this instead of what was there before. The other part, blocking, simply means, the adversary cuts the cable, prevents anything from arriving. And replay, finally, is this thing we also talked about on the authentication way back when, that the adversary sees a message on the network that he finds is advantageous to him. And now he sends several copies of that message in the hope that, more good things will happen if I send more copies here. So in terms of modification and replay, we have cryptographic tools that will help us detect those at least. Whereas blocking, of course, is something that we can't do very much about if we don't have physical control over the entire network, which most of the time we do not. Then, of course, cutting the cable is not something we can really prevent. We can hope to have several different paths from A to B, so that the adversary probably won't be able to block them all, which is indeed the case on the internet, but completely preventing this is of course not possible usually. Okay, so that was X800. Then we have a couple of other classifications. There was one which has a kind of a silly acronym, but I'm told that the sillier an acronym is, the easier it is to remember. So we have the I know classification, and that's supposed to enable us to talk about who attacks us, and so to speak, where do they do it? So the E stands for external, where the idea is that we differentiate between external and internal attackers. So external means people who are not users of our system, external hackers that try to break in, and internal attackers, of course, are users that are registered users of our system, and therefore starts, of course, from a different point of departure and maybe be able to do worse things to us if they are actually malicious. Then we have here, that's the who, and the where comes now. So we have different places where we can be attacked. So one is network attacks. That's the N. So this just means exactly what we just talked about, namely X800. Any attack that can be done by simply accessing network traffic. These are things we have, these are easy to mount. It's very hard to imagine that you could not physically access the network as an adversary. But on the other hand, we also have quite good tools. I mean, we talked about them before. We have quite good tools to prevent network attacks. Then we have offline attacks. So offline attacks are basically attacks that take place while the system is offline. So here, the idea is that we steal data offline. So one thing you could think about here is maybe you were able to steal a hard disk that the system uses. So you'll have a whole bunch of data on that hard disk, and you somehow take this away, take it to your own lab, and try to analyze what's in there. So getting an offline attack to work is of course harder than doing a network attack. You have to break the access control of the system, but you do have your own choice of when you want to do this, to choose the most advantageous moment. And once you get the data, if you want to search a hard disk, you can probably use standard search tools to find what you're after. And therefore, if you want to prevent something, an offline attack, then the obvious counter attack method here will of course be encryption. Make sure that whatever the adversary steals will not make sense to him. But what you have to take care of here is, if the data is supposed to be useful to you, you need to be able to get hold of the key when you start up the system. So you have to ask yourself, what about the key? So where is the key going to be stored is an important question, of course, because if you store the key in the same hard disk as where your data is, then of course there's no value of the encryption at all. So that's something you really have to be careful about. Finally, we have the online attacks, which means the adversary is inside the system while it's running. So think of the adversary being able to install some malware, some process that runs at the same time as the actual system is running, and tries to monitor what's going on the CPU, let's say, while the system is actually running. So that's obviously the hardest attack to mount. You have to completely break the system's access control, and you have to be there at exactly the right time, and you have to know something about how the system organizes its memory, so you can find where is, for instance, the secret key that you're looking for, let's say. So here it's really only the access control and maybe the intrusion detection that could help you against such an attack. So it's the hardest type of attack to mount, but it's also the one with the most devastating consequences because, for instance, it's quite likely that the encryption keys, for instance, or the signature keys that your system is using, will at some point be actually available in clear text in the memory of the system while it's doing, whatever operations it needs to do. So therefore, if the adversary is inside the brain of your machine, he would be able to just read those keys off. So I find that this classification here is actually quite useful in trying to do security analysis of a concrete system, because it allows you to go through first of all, are you actually worried about external attackers, or are you worried about internal attackers, or both? You go through all the different types. Are we secure against network attacks? Are we secure against offline attacks? Do we want to worry about online attacks? Stuff like this. Just so it can sometimes be meaningful in your analysis because of the situation you're in to say, like, online attacks, we will something define that we're not worried about those. It could be the case, for instance, if you're designing a software system that is supposed to run inside some web hotel, let's say, and the guys who run the web hotel, they post some guarantees saying that we have appropriate access control, intrusion detection, whatever, firewalls. So we take the responsibility that nobody's breaking in and is inside your system online. And if we decide to believe that guarantee, we can say, well, for our design, this thing is not important. We don't do this. But offline attacks might be important to us because we might have to download data from our system, and then we have to be responsible for how we store that data, just as an example. Okay, the final classification is more kind of a classification in retrospect. So when the attack actually happened and we found out that something was wrong, then we want to go back to our system and say, so where did we make the mistake actually? So so the question you can ask yourself is, if we look at our three main ingredients, the threat model, and the policy, and the mechanisms. So also known as the TPM classification for obvious reasons. So the attack that we actually got, was that because the threat model was incomplete? Did we actually get an attack that we thought was too unlikely to worry about? Or did we get an attack that we simply did not think about at all? The policy, well, the policy is a specification of which states do we allow for our system, which events do we want to allow. And it could be, for instance, that the policy is so complicated that we didn't actually understand completely what was going on. What does the policy actually allow? If we don't understand this completely, then the consequences could be more serious than we actually thought. And finally, mechanisms, well, there could be some implementation error. Some code just doesn't work the way it was supposed to, and then we get some problems out of that. So this can be useful, of course, in retrospect to look at this for your own system, but also, of course, looking at examples of attacks for other systems and learn from the mistakes that were made in the T or the P or in the M. So this was the end of the first lecture in the subject. Then in the following lectures, we'll look at different examples of attacks and see how they fit in all these models.